Hello. Okay. Okay, let's start. Thanks everyone for joining. I think there are some more people finishing their breakfast who will join in soon. First session's always a little sparse, but anyways, we are really fortunate today to have Professor Sanmi Koyejo. He's a professor at the Stanford Computer Science Department, where he leads the Stanford Trustworthy AI Research Lab, the STEER Lab, and we're going to hear from him about distribution shifts. So. Let's hear from you, Sanmi. Thank you.
Yeah, thank you for waking up and joining early. What I thought I'd do today is give a, perspective style talk. So this would be, I won't be showing many results, but I wanted to engage a bit in some questions that I've been thinking about from other perspectives that I thought could be relevant to distributed and federated learning and heterogeneous learning broadly defined. In particular, I guess I have, like maybe some of you, this interesting observation of being part of different subcommittees that ask questions somewhat differently, even though they're asking quite related questions. So, federated learning folks, I'd say high percentage optimization, some privacy, a few other things. And then distribution shift type community, which is a lot of statistics, maybe causality, like those kinds of questions. And what struck me, in some sense, trying to go back and forth between these two, are, and again, somewhat obvious, but maybe worth being explicit, how many of the kinds of questions we're asking seem quite close to each other. And so today is my attempt, somewhat intentionally in one direction, to state some things that I think we've learned and might be interesting from the distribution shift part of the world, and ask to what extent they are relevant and could be interesting as framings for maybe expanding how we think of some questions in the heterogeneous and federated learning world. And so mostly I'll be interrogating this question of what does IID mean, because that's really the key question that, or non-IID, actually maybe the more interesting one, that distribution shift engages with. The time is set up such that, if there are questions or other, one of those things, please interrupt and let me know how you think about things. Again, this is a much more sort of perspective talk than a result talk, so that's my goal. Maybe see if that's good for early in the morning to get you excited about all the other things that will happen over the course of the day. Okay, so to set things up, just to give one example, but I could have picked, 10 different examples. Here's an example. It's primarily from a distribution shift perspective, but I think it's one of those where the gap from doing this with distribution shift and doing this with federated learning is tiny. So this is in a healthcare context. This was one of the largest computing providers, computing intensive IT providers in healthcare is Epic. So they built a model to predict sepsis. So it's a fairly serious condition, can lead to death. And they did this across a few 100,000 encounters, 3 different health systems, and then released it because they have broad distribution across lots of different hospitals, as a model that anyone could use to help predict whether sepsis might be sort of potential sepsis onset for patients, writ large, mostly in the US. And in the work that they did, they claimed reasonably high performance. So they got AUCs in the sort of 0.76, 0.83 range. For the challenge and difficulty of this problem, this would be considered, I think, a quite potentially useful model. And so it got deployed, lots of people started to use it. And so this was released in 2017, but some of the first analyses, external validations, happened in 2021. So one of these was in Michigan, And they looked at how well the model was working within their particular hospital system. And maybe no surprise, given the talk I'm giving, there was a meaningful drop in performance compared to the advertised performance. So from the sort of 0.7 to 0.8 range, we end up in the sort of 0.63 range. Maybe not noise, but much less useful than where we started. More importantly, in terms of specific kinds of errors I was making, I think it was starting to get concerning. So, missed a large fraction of sepsis patients, alerted for sepsis on roughly 18% of all hospitalizations, so just way over predicting potential sepsis. The sort of prediction rate was too high. And in terms of how much marginal benefit this was providing compared to a clinician trying to make the decision, what they found was roughly 7% additional sepsis that were caused by clinicians at the cost of a ton of additional false positives. So again, potentially worrying. The next year, there was some additional post-analysis. And again, maybe not surprising for this room, but some of the things that we talk about a ton happened or were shown. The performance was not only lower, but actually systematically lower across a bunch of different downstream deployments. For hospitals that had higher sepsis rates of sicker patients or more oncology cases, cancer cases, they actually had a higher or worse performance, which they took, and their interpretation was the model actually worked best where it was least useful, and it worked worst where it was most useful. And so here, I think the key story here is this heterogeneity across patient populations, and maybe some systematic notion of heterogeneity ended up degrading model performance in a way that wasn't caught in trying to build this general purpose model. And so in this room, I think the bunch of experts that would sort of very easily diagnose what happened here. So it's not a surprise to most of you, hopefully. But the very obvious thing, the hospitals that we're trained on are not the same as the hospitals they were deploying on. They trained on a small set. There was some difference between the training set and the broad deployment set across the US. We might call this a covariate shift in the distribution shift world. Covariate because, again, the condition is the same. It's a sepsis problem. We think most of what's different is the sort of distribution of patients that you're looking at. In FL, we might call this some version of client heterogeneity as the sort of key gap that's showing up. In the medical setting, we had sicker patients that broke the model because you had this systematically worse for some of the sickest patients. You might think about this in the distribution shift term as a problem of trying to extrapolate across or beyond what the training data can meaningfully support. You might think about this as sort of out of federation clients, or again, out of distribution clients potentially on the federated side. Some of the the reasons that these issues happen is that they didn't do enough site-specific validation. So they didn't pre-deployment at new sites. They didn't do enough work to check, does this work in my hospital context? They just sort of took it at face value, which is extremely reasonable, you can imagine, for many hospitals. I mean, they're not necessarily, what they do best is not build ML models. You have this big provider that says they've solved your problem or a meaningful problem, they give you a model, you would just run it. And so this lack of testing to see whether it actually did what they hoped it would do in the real world is, again, an obvious issue. We might think about this as personalization, as some of the gaps that show up in FL setting. And again, the core problem at the end is that they try for this one-size-fits-all deployment. So they ignored the differences across the different hospitals in this case. And so potentially, or maybe not surprisingly, you might think about this as ignoring what we would call non-IID structure in most of the lecture, or the workshop this week. And so maybe somewhat obviously, but just, again, to be pedantically clear, these kinds of failures show up constantly in distributed and heterogeneous learning settings. And I guess there's a concern that we're maybe not rich enough in how we're thinking about the different potential failure modes and what we can be doing to mitigate some of them. So, there's some maybe, I'm putting these as quotes, but you can think about these as like, I don't know, throwaway lines that you could imagine that people might have said. That may or may not completely fix some of these issues. So, just train on more data, maybe, or run more rounds of whatever your favorite algorithm is. I put Federated, the OG up there, but you can pick your current favorite. Claims about global models working everywhere, which I think we secretly believe in FL, even if we don't always say it, just based on like what people are actually doing. This challenge of heterogeneity being like insufficiently precise and insufficiently clear about the particular issues that are showing up, which is what I'll spend most of my time today. Just sort of, the translation here is, again, the general framing of non-ID is one problem. And then some of the gaps in evaluation and capturing signals about what might be different across different clients. So again, there's some sensitivity to this, but I think there are meaningful gaps here, and I think opportunities for learning from some of what has been done in the distributed learning, in the distribution shift world. So lots of different methods. I think many of them great work capturing various aspects of heterogeneous learning problem. But with respect to questions related to distribution shift, it's often unclear which heterogeneity regime each of these existing methods might be solving. And so potentially our understanding of a problem is behind our willingness or interest in providing new methods. And that gap can cause issues because we don't know when to apply what methods where. So again, this is a perspective talk. So I'd love to know where I'm wrong on this. This is, again, some thinking. But the framing today, first I'll talk about evaluation and benchmarking, and some hypotheses about what I think might be happening in at least many of the benchmark data sets. I'll shift gears and talk a bit about the optimization methods and what they're targeting, and to what extent we think that there might be gaps for the nature of heterogeneity in the real world. And then I'll make a small pitch for some more measurement theory kinds of ideas that I think could be helpful to both understand the issues better and potentially help us better compare methods in appropriate contexts. Okay, so first, heterogeneity, from my perspective, means many different things. Many people have come up with taxonomies. I won't exhaustively go through them, but there are at least 3 regimes that make sense to me as sort of somewhat clear regimes. Again, there will be stuff in the middle, but bucketable kinds of non-ID-ness that you might imagine. So one is our settings where, of course, your test data is different, but some kind of interpolation would be sufficient. There are settings where test data is different, but maybe your feature learning does a good enough job, and so mostly what you need is some kind of adaptation. And then settings where the test distribution is far enough that you need either much stronger structural assumptions or much stronger interventions to have good performance in attempting to generalize to those settings. And so most of this framing comes from the distribution shift world. Again, I've seen versions of this I cited one of these, good paper from ACM computing surveys recently from Ye et al. On thinking about heterogeneous federated learning that tries to engage with this. But again, the main claim here is different. Non-ID is not one thing. It's at least 3 things and maybe more things. And it's worth thinking carefully about what context one is in order to figure out how to measure things and what methods are appropriate in those settings. Okay, so the first, maybe the most easiest setting, and I'd argue that this is where we are in a lot of the sort of foundation modeling foundation model style of work, and arguably where most of the field is, so for better or worse, is trying to get everything in the world to look like interpolation. So trying to get sort of good enough coverage with our data such that test data looks like it's within the same distribution as the training data. There's a little bit of technical work on this, and also just very clear, obvious empirical evidence that if your test data is close to your training data, then even if you're in a sort of multi-distribution setting, either in the sort of classic distribution shift sense or say in the federated learning sense, doing ERM is the right thing to do. So essentially like just collecting your data together and training like you didn't have a distribution shift problem is, in some settings, provably the optimal method, even in a stronger sort of minimax sense. This paper has some good discussion of this. So what is nice about this is if you're in this context, you don't need any special robustness. And standard training is fine. I'll talk more about this in a little bit, but I'll also argue, this is maybe very slightly controversial, that this is also the regime where a phenomenon called accuracy on the line shows up. Are folks familiar with that idea? Have you seen this? Okay. So accuracy on the line is a fascinating, to me and I think to many in the community, idea. It's an observation that for many real-world distribution shifts, there is a strong correlation between in-distribution performance and out-of-distribution performance. And in fact, almost linear correlation between in-distribution and out-of-distribution performance. So this has mostly been shown, a lot of the initial work was empirical. People looked at a bunch of different problems. They fit different models. They looked at what happened, within the training, like standard train test split within distribution, and then for the same kind of problem with a whole new data set that's collected conceptually where you'd expect some meaningful distribution. What you want to do is ask, for a particular model, so you play with a whole bunch of different model architectures, other things that you might tune about either a model or a family of models. What is the correlation between model performance in distribution, standard train test split stuff, and then out of distribution with some kind of generalization? And one of the key observations from now, I think, many papers empirically, and then a few papers trying to engage with this conceptually as well, and theoretically, is that there's a strong linear correlation. So why this is useful? One, it suggests maybe distribution shift is simpler than one might imagine. So that's hardening if it's an annoying problem and you'd rather not be thinking about it. It also, I think, is very useful because it allows you to maybe, more than just a high-level distribution shift might be simpler. As an actual decision-making tool, what it says is that a good way to optimize for some unknown downstream distribution shift when I deploy my model is to just make sure I do as well as I can in distribution, because this linear correlation says models that do better in distribution will also do better out of distribution. So this is great. This just says, and I don't need to tackle out of distribution directly. I can just tackle in distribution as well as I can, and I should get some strong extrapolation to out of distribution performance. So somewhat well established for a variety of different data sets. I'll come back to this in a little bit, but a claim that I'll make, and we've made formally in a paper I'll show in a second, is that this seems to be true when the shifts are somewhat simple. And the more complicated the shifts are, the less likely that you see this correlation. Yes?
Just make sure when the Q is in the sort of like, what do you mean by ERM? Are you just thinking of the average of these things? Because intuitively, I think we should solve the min-max as
yeah, so this is this paper engages with that. The fascinating thing is that it says collecting all data in one pool and training against that is competitive with the min-max. Okay. Yeah, so ERM actually is good if like things are in convex hull. Yeah. So it's both surprising and not surprising at the same time, I think. I mean, the formal statement seems surprising. It's worth digging. I won't, unfortunately, I didn't do, like I said, I decided not to do technical detail here, but happy to chat more offline. But the formal statement is that yes, ERM is competitive with min-max under the assumption, the convex hull assumption. Okay. So, some conditions under the hood, the big one being the sort of convex hull assumption, but this is roughly equivalent to a coverage assumption. And you need your loss to not be too crazy. So all the standard like Lipschitz things.
So do they also assume the tasks are simultaneously realizable or something like that?
This is a good question.
Then I can see why.
I don't remember, actually. It's a good question. Yeah. I don't remember if they made realizability assumptions. I will defer and check. Yes.
Not to make a segue that's too pedantic, but what is the definition of distribution here? Because like, in the sense of if distribution is like an empirical finite set of samples, then I could see it shifting. But in some sense, the argument here was if distribution instead means some underlying statistical process, there's really no shift happening, right? It's just saying that train and test are just different finite samples from the same underlying common distribution in a sense, right? Like, I mean, I guess I'm saying you could almost make an argument here that there is no distribution shift, right? There's
Yeah.
Different realizations that are from the same, I know, the data generating process.
I hear your point. There is a construction, maybe I'll soften what you're saying as like, there's a way to think about this as almost a mixture process, like sort of generating within some large, I don't know, some, I guess the overall population being within some support, and then you have like train data that is sufficient to, sufficient coverage within the support, and then test data like maybe new mixtures under the same support, something like this. There's a version of the argument that can be population, there's a version that you can make empirically. I'm not being super precise here. I also like need to remind myself of the specific details. So this is good because I always forget that at Simons I should be very, very precise about math things. Go ahead. You might.
What difference does it make if we call it distributions or not?
Yeah,
I think it's the.
That's why I said I don't mean to.
I don't know if
The word
it's.
distribution.
I guess I meant like there's a lens that you could look at this and
Right.
there isn't any shift happening. It's all like there's some common.
Well, I think I was engaging with the tooling would look different.
We do know that there is a change between the training data and the test data.
There is a change within the train and test.
So the test data is different potentially,
Sure.
right? We're
Okay.
knowing that there might be a change in the test population, in the test data. That the test
I mean,
data
even
is
with
not
the
going
finite
to
sample,
exactly
sure.
to the training data.
Okay.
But if we do know, if we want to allow, if we want an algorithm that can be robust to a change at the test time, then it's fine to just call it, to view it as a change in distribution, right?
Okay, yeah, sorry, maybe we could talk more about this.
Yeah.
I don't mean to derail this. I think maybe it's what's the definition of change? Because in some sense that here it feels like change is a very predictable, minimal thing.
I think that's sort of the key point, is
Yeah.
that change is, I mean, if you want to distill down to, I don't know, intuition, is that the change is benign in some way. And I guess the stronger version of this claim, or an extrapolation of this hypothesis, if I wanted to tie this closer to, again, our modern practice in machine learning AI, is that I'd argue this is a lot of what we're trying to do writ large with foundation models, is that we're trying to get everything to look in distributions such that we get this kind of property. I actually do think so I guess I was engaging, like I said earlier, I think the specific way you show the result will look a little bit different, depending on whether you think a population version of an argument or like specific data samples. But yeah, I think the broad intuition will still hold. Did you have a comment or question? No? Okay. Okay. So translating this to federated learning, a claim, this is again mostly based on the observation, though I wonder if someone has done this formally, is that most of our federated learning methods target the ERM solution, yet work actually really well, even in settings when you think you're inducing some distribution shift. So actually it's a quite competitive, ERM type solvers are quite competitive baselines, even with some kinds of distribution shift. And the argument is, in order to see a gap, you actually need, so if somehow you're creating new clients, but all the clients have data that is sufficiently close to your training data. So in particular, what I'm thinking here is most of the ways that we curate non-ID is actually not a data distribution argument, but like a subsampling argument. Like we subsample a large data set in different ways. To actually induce sufficient gaps to get a distribution shift could be non-trivial. And so very easily you can construct a setting that you call non-ID, but actually from a learning, particularly statistical, but seems also optimization perspective, it effectively is ID. Of course, some of the original methods and the advancements on those methods, like the particular optimization issues that come up with having data samples of different sizes that you need to fix, and so some of the optimization methods help fix some of those issues. But the argument here is that they're not that good, not necessarily engaging with an underlying population shift problem. They're more engaging in maybe simpler, more benign kinds of shifts. So again, I don't have a clean, complete answer here. A lot of the thinking comes from the distribution shift world, but I think it's an interesting question to better characterize in what ways this question might be different in a federated learning setting compared to a standard distribution shift setting. And maybe a stronger provocation is that, again, many of our existing benchmarks, many of our existing algorithms may work as well as they do and be so hard to beat because implicitly our test settings are just not hard enough. And if you think the real world is closer to a more complicated, heterogeneous setting, then you should be training and testing your algorithms much closer to that more complicated setting than effectively the coverage setting. Okay, so there's a bunch of existing tools around that. If you shift a little bit from the simplest setting, there are also settings when we think the problem is there are shifts, but we can engage with the problem via adaptation. A few methods already exist in the distribution shift world. So one, there's a bunch of work showing how fine-tuning can be an optimal strategy. One that ERM is actually quite good often at learning representations. And so if you're in a setting where the representation is sufficiently transferred to your test domain, but the actual predictor might be different, then fine-tuning is a good strategy and can be an optimal strategy. And so, again, a bunch of work in the standard distribution shift world where you might do fine-tuning in the simplest setting, use some domain adaptation methods if you need to actually align the representation. So just you don't get it for free because maybe you don't have enough data, or the representations really are a little bit different, but different in a controllable way. So it sometimes is helpful for some covariate shift settings. Or various kinds of proxy methods. So this is useful where there is some latent structure. The shifts are controlled by maybe some more complicated latent variables, but you can still model and correct for it using various kinds of proxy. These proxy methods come from the causality world that have been quite useful for distribution shift settings. So the main claim here is more complicated than the simple coverage setting is the adaptation setting. When the shift is structured, there are good methods in distribution shift to handle this. So various kinds of adaptation approaches, things like covariant shifts, label shift, even more complicated proxy or latent shift techniques. Of course, there's a tension here, right? Because we're always trading off how well we can do, or how well we can get methods to generalize against how well they work in new clients compared to how well they work on some existing data set or data distribution. And this shift can be significant. I'm showing here an example where this is a clinical cartoon of a setting where you might want to generalize from some parts of the world, say the western parts of the world, the US and Europe, and you're trying to generalize to parts of Asia, Southeast Asia, or Africa, where we know that there Like the clinical conditions, underlying clinical conditions are the same in principle. There are lots of environmental factors that are different. There are care factors that are different. There are a bunch of specific factors that are quite different. And so there's this gap between building methods that just have sort of good generalization built in versus trying to think about how to improve the methods against local predictability. So again, bunch of tools. Many of you have been part of work that has either tried to build personalized methods, so various ways to either from scratch, but exploit some shared information, or I'm a big fan of a bunch of these methods that start with a global objective and then do some local fine-tuning. It's very simple, actually can work really well. As a way to interpolate some of the extremes of a single global method that works everywhere versus trying for local methods that work in the context that we need them to work. But to engage a bit in how one maybe picks objectives and how one maybe picks, like how I actually formalize this problem. I think the tension shows up in how we pick both learning objectives, how we evaluate work, new work in this area. There was a time where, I mean, a bunch of the early federated learning papers I think had no shift at all. Like they're, you know, or at least the data context that people applied it to was essentially just like subset data in a naive way. At some point, all the reviewers started to require that you create at least unbalanced data distributions across the different clients, so which is good, I think. Trying to be more ecologically valid, so capture a little bit more of the real world structure across shifts. I think as the standards for the field correctly went up, they seem to have lost some nuance, and the way I'm engaging with this is, again, there are a bunch of different kinds of, I've shown at least 2 or 3, so different shift types. Simply asking that the data samples not be the same across different subpopulations is not precise enough to engage with what you might think is a meaningful kind of shift for some deployment context. More than this, if what you want is a sort of globally good model, then you should test against that. If you only want is sort of locally good models, then you should be testing against that. I often see papers and review interactions that conflate the two things. So is the objective global? Is the objective sort of local best effort? Again, those things can be in strong tension, and maybe being more precise about what we want and then building methods against those is a more productive route. Okay, so yeah, I think there's some interesting space here to better characterize the Pareto frontier. I'm showing one of, there's a paper a couple of years ago that tried to analyze the sort of train and fine-tune method and showed that it can be optimal in certain settings. But I think the general provocation is, and maybe call to action, if you like, is better characterization of this gap and maybe cleaner analyses in what we're building and evaluating across models.
So I just want to understand the difference between regime 1 and regime 2. So should I think of regime 1 as maybe P of x and P of y given x both are sort of shared across the tasks, while what you're trying to say in regime 2 is that P of x is potentially different, but P of y given x is shared across the task? Is that
Yeah, so in, when you say regime 1 and regime 2, I think you're talking about the sort of convex Hall setting versus the adaptation setting.
So in the second setting, should I think of P of y given x being shared across the task?
So in the second setting, P of y given x is not shared, but the simplest version of this, P of y given phi of x.
P of y given phi of x.
Actually, like phi of x is shared. So there exists some representation that's equally good across a whole bunch of different tasks.
I see.
But you need to learn local mapping.
But if P of y given x is shared, there's no tension, and then there is no.
Yeah.
But you're saying that the learning phi itself induces a tension, and there might be a.
I'm saying that, so the tension comes from,
So is this like a feature learning issue or like a concept shift issue is what I'm trying to understand?
it's a little bit of both. So in terms of intervention, One of the, again, most common interventions is, again, like exploit the fact that ERM on a sufficiently rich data set will give you a good phi of x, so it will capture that. Actually, let me step back and talk about, so this paper, last layer retraining, I think is an interesting one. They went the other way, but I think there would be an interesting way to frame some of what's going on here. So for them, what they were doing was they were looking at the broad literature that tried to build robust learning methods to spurious correlations in distribution shift world. And what they argued and what they showed was all of the methods were beat by training a single model on all your data and then fine-tuning the last layer to your specific sort of downstream subtask. The argument here is that this worked because there were many of the data sets that we were looking at were in a distribution setting where what was shared was the representation and what was different was P of y given P of x. And so how do you learn this P of y given P of x? Now, this is a maybe structural implementation framing of the result. I think it's interesting and useful. The way that this shows up in maybe conceptualization beyond what the distributions might be and what you're trying to learn. The other question is, what do you, like, on the measurement and evaluation process, how do you think about that measurement and evaluation? So if I evaluate using only, like, global performance, I'm very likely to miss the fact that I have some of these, like, distribution shifts across the different. I'll make an even stronger statement. Methods that are globally robust are often worse locally, because spurious correlations can actually help you locally. The globally robust models will try to remove as much spurious correlations as possible. So to ground this, I am in a medical, I'm building a sort of medical predictor, and it turns out that, I don't know, the condition is very tied to weather conditions. Weather is not necessarily a biological variable. In a like causal medical predictive world, I would want maybe not to use weather as part of the predictor because it's a little bit spurious. But in a local context, using that additional information actually helps you a ton to make a good predictor. So the spurious information is good for local predictors, bad for like a globally robust predictor. So on the modeling side, this says you should build models to sort of target one or the other, and there are ways to think about this. On the evaluation measurement side, it says if what you want is to evaluate global robustness, then you should evaluate global robustness. You should know that you're often giving up something about local adaptation. And if what you want is to measure local adaptation, then the evaluation process should engage with local adaptation and know that you're unlikely to be building a model that's globally robust in a general purpose way. So that's the trade-off I'm trying to highlight. Yes? No? Okay. It looked like a beginnings of a question.
Yeah, well, I did, but I was swallowing it, but I'll ask. So the latent structure, the third row, in some sense, is that a intelligent converting regime 2 to regime 1? In some sense, is it sort of like by taking advantage of some low-lying, previously unknown, whatever, structure, you now can say, well, this is an adaptation, this is interpolation. Is that... Is that what that means, or does it mean something different?
So mechanistically, regime, the proxy methods are useful. I'll try to engage with your question. I haven't thought about it precisely this way, just so I don't have a clean answer. But mechanistically, the proxy methods are good. They capture complex shifts that are sort of neither purely covariate shifts nor purely label shift, but like shift uses some additional variable, a third confound variable, so maybe spurious, but other some additional thing. And so graphically, you can throw up a causal graphical model that sort of captures this thing. And if you have a proxy of that and some other information about your generated distribution, then you can correct for it, either in a generalization sense or in an adaptation sense. Okay. If you're doing it in a generalization sense, then I think your analogy is apt. So it's like
taking your weather,
right, deconfounding against.
You're basically changing your convex hull to incorporate this data, and now now you have an interpolation regime. for?
I've never thought about it that way. I'm willing to hand wave in that direction. I want to be careful about, yeah. I think that's a reasonable analogy if you're trying to build. So you know, the actual thing you're doing is that you'll be correcting P of X's to make them look a little bit like they're within the same home. I think that's a reasonable analogy. Cool. All right. So let me go to the, I think, most complicated case where you really are trying to do way out of distribution generalization. And here, so far, most of what we've seen suggests that without some kind of structural assumption, they're not great tools. So what breaks here is you can't rely on your earlier training method to either just give you good predictors for free or give you a good representation that you can then adapt, which is in the first two settings as good ways to construct the learning problem. And so most of the work that I've seen in this area and how we've engaged with it tries to then think through what might be good causal or invariance assumptions and then build models that explicitly use those kinds of assumptions. Here the trade-off, of course, is that you now need to make somewhat stronger generative assumptions in general. And so you hope you can know something about the setting and context to figure out what the right generative assumptions are such that you can then build good learning strategies for those settings. And so there are a few of these approaches out there. I think that the key thing I wanted to say was within the federated world, we throw everything as non-IID. I think, again, there could be quite complicated nuances and differences about what's different across different clients. And so the maybe slight provocation here is, again, thinking through how to bring in some of the best ideas maybe in the distribution shift world in how we both build methods and then, as we've talked about a few times, evaluate methods for various kinds of more complicated generalization settings. So again, I'm showing some of the simpler settings here for contrast, but the key idea here is there's a setting where you get generalization almost for free because essentially just like collecting data together will look like convex hull, you just train. There's settings where you get representation learning for free or stuff close by it where you can think of adaptation as like, I guess I'm defining it by strategy. But effectively, the intuition is that distributions are not so far away, and so adaptation is a good method. And then there's settings where, when distributions are sufficiently far away, where I don't know of a off-the-shelf like training method that doesn't require some generative assumptions. And so far, mostly we've been using causal assumptions as a way to frame these kinds of problems. Okay, so just to repeat, so interpolation settings, adaptation settings, generalization settings. There's some FL strategies that engage with some of these problems. But I think, again, being more precise about what non-IID means gives the opportunity to also be more precise about how we build methods and then hopefully answer and deploy tools that are much more useful in real-world settings once we can identify which of these settings we're closer to. Okay, finally, maybe I'll do some provocation around evaluation and benchmarking. So some of this is tied to just literature. Some of this I'm learning more about, and I think many in the field are engaging with. In the measurement science world, there's this idea of construct validity, which is this question of designing evaluation processes and benchmarks to measure what they claim to measure. And so thinking through this idea of worst case heterogeneity or worst case non-IID-ness, a good benchmark for this should distinguish methods that handle distribution shifts from ones that don't, penalize methods that don't work only under benign shifts, like the sort of interpolation regime I talked about. And importantly, and I think where we've been trying to anchor a little bit, is that if you set up a benchmark, but it's actually solvable by a simple interpolation method, like an ERM method, your benchmark is probably not capturing the kind of complex out-of-domain setting that you think it might be capturing. So again, slight provocation, but when I look at a bunch of the benchmarks in federated learning, of course, things have gotten better, but I don't think they've gotten that much better from, say, I don't know, early 2010s or mid-2010s, where a lot of the benchmark data sets still look like variations on taking one data set and then like partitioning it in a non-IID way. So the sampling is non-IID. You hope that this induces some non-IID structure. But we're not systematic or clear about the specific kind of non-IID structure. And we're not necessarily capturing interesting notions of distribution shift that might show up for clients in practice. And so, most papers are still variations on CFAR or maybe other data sets, but mostly using the standard Dirichlet style like subsampling partitions. There's no equivalent of something like a Wilds, even though, again, I think there's still space in the distribution shift world to have more complicated benchmarks. And so there's been lots of work, I think great surveys on heterogeneity types. I'd argue, and I actually love to learn if I'm wrong on this, but I'm not aware of operationalizations of these ideas into evaluation strategies of benchmarks that meaningfully engage with all the different ways that we think we can have complex variation across populations when we're deploying methods. Is anyone immediately please?
Two comments. One,
okay.
that's not mentioned here, but is I think better than others at heterogeneity is iNaturalist. Marco in his talk on Tuesday or Wednesday.
Oh, cool. Okay.
It's an image data set, but it's a lot more disjoint, I think, in terms of content.
Okay.
But also, I think to your broader point, I agree. And also, because I guess the problem, if you're homogeneous, there's one definition of what that means, but you can be heterogeneous
in many different ways. I think that's better said than I.
Because when you've been talking about heterogeneity, most of my day-to-day problems are with language models. So I tend to think of language as my natural heterogeneity, but image heterogeneity is a totally different animal.
Indeed.
So I think part of the problem is probably having better heterogeneity, but then that requires many different data sets in different domains, I think, to capture.
That's accurate. Yes, I think that's accurate. Yeah, I knew about some of Marco's work. So, this is your paper, right?
No, it's the benchmark. I think is from Google actually.
Okay.
But we showed that some of these methods they don't work on this realistic benchmark, and yeah.
Yeah. So I like the way you framed this. Again, homogeneous is the same thing. Non-homogeneous can be many different kinds of non-homogeneous. I think that's maybe the key point I'm trying to pitch today. And I think trying to be more precise, both in modeling, optimization, but also evaluation of non-homogeneousness is helpful both for scientific understanding, but also I think more meaningfully engaging with practice and problems that show up in the field. I think I'm tight on time. Remind me. Okay. Okay. So I'm mostly done. I'll maybe point to this paper where I'd love people to take a look, where we argue that if you see accuracy in the line, so if you see strong correlation between in and out of distribution shift, it's probably a really strong signal that your benchmark is not heterogeneous or hard enough. And so it's actually like a negative signal for trying to get at the point of true out of distribution generalization. Okay. So better regime identification, more emphasis on discriminated power, negative controls, so actually checking that you can't just solve it with an interpolation method or a method targeting ERM, and then getting maybe closer to interpretable heterogeneity metrics. Okay, I will skip. This is a general purpose open problem discussion, and maybe just spend a couple of minutes on the end. I think, again, there are some nice lessons that potentially can be learned from the distribution shift and measurement literature for federated learning more broadly, and heterogeneous learning more broadly. And so I think interesting questions around distribution shift theory, started to characterize things, but I think there's still many gaps. And again, always the goal is to better characterize the signal so that we can engage in what happens in the real world. Better federated learning methods that capture a whole bunch of these kinds of complicated settings, and better measurement tools to capture, to actually make sure we're measuring what's actually going on. Non-ID is not one problem, it's many things, and we should engage with all those things. That's it.
Maybe we have time for one more question, but there were lots of questions in the talk. Any more questions?
Most of your intuition is based on distribution, or as I was saying, sampling from distributions, but not necessarily a model is able to see that distribution. Maybe optimization doesn't allow to optimize and see and capture the whole distribution. So how to combine and link what the model is actually able to see and the distribution that is able to acknowledge as in distribution or out of distribution, and what is a distributional property of the data itself.
Yeah, so I'll refine you. I don't completely, what I understand from your question is like how to tell maybe which setting you're in and how to build models against those settings. So a very short, like I guess, in the direction of an answer, I think measurements can be a very useful tool here. So to first order, I think one way to just characterize which kinds of methods work well in what settings would just be having measurement practices that better disentangle all of these different downstream settings. So this would just allow us to do better evaluation. So that's sort of one version of it. There's a separate question here of like, how do I build models that can maybe adaptively deal with a whole bunch of different kinds of settings? I don't know that there is one method. I think what we have right now are regime A here is a good approach. ERM is competitive. Regime B, you should do adaptation. Regime C, either build models or maybe train separate. Either make very specific assumptions and build causal models, or train separate models effectively. If you have like distinct enough structure across the different models. It's a great question if there is one algorithm that can adaptively handle all these. I don't know of a method like that.
Let's thank Sanmi again. Okay, so now we have the open problem session. So just to make sure, we've stopped recording, broadcasting, everything else. So feel free to be very provocative and anything you want to do. So I think we're gonna probably